Hi students. So today we start optimization tutorial 7 and we are now going to start looking at a series of methods which essentially find the step size by doing minimization of a one variable function. And essentially if we find the appropriate step size, then we know how much to move in the descent direction. That's the aim of all these methods. I'm Dr. Ganguly. So in today's lecture, we are going to look at probably the simplest of the methods to solve this problem of minimizing the unimodal function, and we are going to bracket the minimum point, and then we are going to refine this particular bracket, and also I'm going to present to you Python code which can solve this problem in a nice manner. Now if you are not familiar with the method, you can look at optimization lecture 7, which essentially gives you the theory behind this method and also the optimization playlist for the full course. Now the first question is to bracket the minimum function given by this equation here, and the step size you are asked to take is delta is 0.05, and then we have to calculate the value of that particular bracket, the length of that bracket, and we have to find the approximate minimum point. So to do this problem, what I have done is I have taken recourse to some calculations using Excel, and what I do is that I calculate the value of the function at different points given by delta, 2 delta, 3 delta all the way forward like this. So for example, I start with 0, the value of the function is 1 at that point, which you can see clearly from this because it's going to become 0 plus e to the power minus 0, which is 1. Then I change this value by 0.05, and then this becomes the new function value, and I proceed in this way forward. So what's going to happen is that the function value is going to decrease, and then you are going to reach a certain point, in this case zero point 0.4, where the function value has started increasing. So these 3 points which I have shown in red here correspond to the points q minus 1 delta, q delta, and q plus 1 delta. So essentially once we locate these 3 points where the change in the function value takes place, we have bracketed the minimum point. So we have found these 3 points as 0.3, 0.35, and zero point 0.4. Now we know that the minimum lies between these 3 points, and we can refine that and proceed further to see where the minimum lies. Now if we were to plot this graph, you can clearly see here that it's essentially these 3 points here, the last 3 points in red, and you can see the slight change in the function value which is taking place. It was essentially going down all the time, and then at this point, which is q delta, it started going up to q plus 1 delta. Now as far as this algorithm is concerned, the advantage is that you can go forward and then you can stop the moment this function starts changing its direction. So you do not actually need to calculate all the points out there. You only need to calculate the points till which the function value keeps going down, and the moment the function value starts going up, you can essentially stop it and you can bracket the particular minimum point. So we have bracketed the minimum point between q minus 1 delta and q plus 1 delta, and essentially this distance here is given as zero point 0.1. So this is given as I here. This tells us how much the bracket has come down to. So this is very important because as far as this algorithm proceeds, we can monitor its convergence by seeing how I is coming down. And if you are not familiar with this method, make sure you take a look at optimization lecture 7 for an explanation of the algorithm. So in that lecture, you will see that why once you have bracketed the minimum, it's possible that the minimum can lie between q minus 1 delta and q delta, or between q delta and q plus 1 delta. That is why we have to consider the lowest value here and the maximum value here as bounds for this minimum point. Now you can get a hint or an approximation about the minimum point by simply using the fact that the minimum point is going to be between these two bounds. So we use this formula here, zero point 0.5 into the lower and the max value, and that immediately gives us 0.35. So 0.35 is the value I get in the first round of this method, and that's actually pretty close to the exact solution, which is alpha star is 0.351734, which we obtained in tutorial 3 using optimal criteria, that is by setting the derivative of the function to 0 and then solving the equation which actually gave the solution in terms of the Lambert W function. Now if you have not seen that tutorial, make sure you see it sometime soon. Now we need to proceed to the next step, and what happens in the next step is that you should reduce the delta value. So here I am simply dividing that previous delta by 10. So previously we had 0.05. So now we take 0.005 and we repeat that same problem. So in this case, what happens is that now the bounds I have are zero point 0.3 and zero point 0.4. So I start from zero point 0.3. I no longer have to start from 0. And then I go forward till again I get that change in the direction of the function f of alpha. So again what happens, the function f keeps decreasing, and you can see at a point between 3.5 and between 0.355 the function has started increasing. So this particular point is corresponding to alpha u is q plus 1 delta, the middle point is the q delta, and the lower point is the q minus 1 delta. So now we have actually bracketed the function between 0.345 and 0.355. So these two values which I have given below or at the bottom of the slide, these are the ones corresponding to the new bracket. Now once I have obtained this new bracket, I can very simply obtain the new value of I, which comes to 0.01. So that's gone down quite nicely. And also I can find the new value of the minimum point, which has again come to 0.35. So again, this 0.35 is very close to the approximate solution. But because we were actually using the values zero point 0.3 and zero point 0.4 in the previous step 1 of this problem, the solution actually has come out to be the same as the previous step. So this is particularly for this function and the bounds we have taken. There is no special thing being communicated here by that, but because we have not been able to reduce the function further or get closer to the actual minimum point, what I'm going to do is I'm going to try to reduce this delta further. So in question number 3, I reduce the delta once more and I get to 0.0005, and then again I have to look at this function and see how it behaves. So from the previous problem, we had obtained the lower bound as 0.345 and the higher bound as 0.355. So I start with that lower bound of 0.345 and I continue moving forward with deltas of 0.0005. That means I take the first value, I add 0.0005 to that value, I add 2 into 0.0005 to that value and continue like that until the function value starts going up. So you can see the function value is going down here. I plotted that same thing on this graph here. And then between 0.3510 and 0.3520, the function value has gone up. So again, these are the last 3 points here. And these points in red correspond to q minus 1 delta and q plus 1 delta. So these are the two ends of these points in red. And so I've been able to bracket the minimum now between 0.351 and 0.352. So let's see if that's a good answer. Of course, I have now these two new bounds for the minimum point, and I can immediately obtain I as 0.001, and I can obtain the value of alpha star as 0.3515. So this is again certainly closer to the minimum point. We see that alpha star, the exact minimum, is at 0.3517, and we are now quite near this value at 0.3515. Now what I'm going to do is I'm not going to any more work on reducing this particular bracket here, but we are going to look at how to write a program, and then we are going to use some of these values to compare that program. So doing a problem by hand is always useful, because once you have done it by hand, here I have of course taken help of Excel to do that problem, but I have certain numbers with which I can now compare my program when I write it. So question number 4 is to write a Python code to create a code essentially for this method here. So that's what we are going to do now. So we are again going to test it with the same function. So let's try to write this code. Now, if you're not familiar with Python, of course, you can use the programs here to learn Python also, because these programs are very simple. So the first thing I do is I create two functions here. The second function is the one which is very easy. That simply returns the value f of x, which corresponds to the function x here. So the function is x square plus e to the power minus x. Now, of course, in Python, if you want to get the exponential, you have to call something called numpy. So I'm going to include that in the main program. So I have defined numpy as np. So np.exp, it essentially gives me e to the power x. Now this basic function which I have written here, this actually does most of the work in the problem. So in this, what I do is I give it delta, I give it some large number n till which it can keep going forward. I give it the minimum point, that is a star, and then I give it a, which is going to be the starting value of the leftmost point. And then I, of course, is the difference between the max and min values, which I have obtained by bracketing the minimum point. So then I go for q is from q in range n, that means q will go from 0 to n minus 1, and I calculate the values of the lower bound, the midpoint, and the max point. So essentially these are AL, AM, and AU, and these are going to be A plus Q minus 1 delta, A plus Q delta, and A plus Q minus Q plus 1 delta here. Now I put a if condition here that if that function value at this point, the third point, is greater than the function value at the midpoint, and the function value at the midpoint is less than the function value at the lower point. If this condition is satisfied, then I can immediately calculate the A star, which is the approximation to the minimum point, and I can also calculate I, which is the distance between the max and the min values of this particular bracket. And then what I do is I define this particular variable a as al. So essentially I have moved the left hand side from 0, where it starts with, to the current value of the left hand side here. And then I print the values of delta, I print the minimum point or the estimate of the minimum point, and then I print I here, and then I break at this point. So essentially if I have found this particular situation, this if is valid, then I get out of this loop here. So this will help me in clearing out of the loop in case I have achieved my condition here, that is I have bracketed the minimum point. I have bracketed the minimum point. Now of course the second function is f of x, which simply returns the function here. So this is something we are going to do. Now in this particular function, you are seeing that some of the values are coming in and some of the values are going out, but I am getting all the things printed right here. So I really don't have to bother too much about things. Now, of course, we need the main code, and in the main code, what I do is I, of course, bring in numpy as np. I define some of the starting numbers, such as delta is 0.05, n is 10,000, tolerance is a small number 0.0001, at which I essentially stop this method. I starting value is 1. I have to give some starting value, so I give 1. And then I go through this 15 times, and of course, it's not going to take all the 15 times to converge this problem. But let us say we have M15 as the max value at which you can loop through this process. A star is the minimum point. Again, I need to define some number here for Python. I give it as 0. And A, of course, needs to be 0 because we are starting from the leftmost point as far as the x coordinate is concerned. So essentially that is 0. So I go for A in range to the max value, that is 15. So I have to create a loop of 15 times here. And then whatever this loop does is that when I is greater than this tolerance, that means when I will be greater than 0.0001, it will essentially bring this function, and then it's going to divide the delta by 10, and it's going to keep doing that. And after some time, hopefully what's going to happen is that the point here or the specification here is not going to be satisfied, and then you are going to be done here. So the moment I becomes less than the tolerance value, this algorithm is going to terminate. So that's the termination criteria. So now let's see how this runs. So essentially I have given you here the case about running this thing, and you can see how this was essentially running. So if I call from the main program here, I have this delta is delta by 10 here, and you see it starts from 0.05 and it locates the minimum to 0.35,
just like it did for the problem we did by hand. The second round was 0.005 delta, and I got the minimum to 0.35 once again, but the I value keeps going down. The third point is 0.0005 and I got 0.3515. So you can go back and check that particular value out. And again, the I value has come down further. Now here, of course, though the theoretical number should be zero point 0.1, should be 0.01 and should be 0.001, what's happening here is that some computational things are happening because of which you are getting this kind of math round off and so on. Now one more round is here which I did not do by hand, but of course the computer does it, and then I get the solution as 0.35175, which is almost equal to 0.3517. And now this thing has been reduced to a very small value. It is below the tolerance. So as far as the algorithm is concerned, it has stopped. So though I have given here 15 to be the max number of times it can go through this loop, it stopped after only 4 rounds of this loop. So again, this is a very simple program which I have written for solving this particular problem in Python, and I wrote this in Google Colab. So you can also check out Google Colab, which is I think a free tool where you can write programs in Python out there. I like these kind of online resources because then I don't have to download anything, but your mileage may vary. So let us now terminate today's lecture or tutorial. So again, we have looked at this simplest method as far as the optimization of unimodal functions are concerned. We have written a Python code for that. Now methods like the one we discussed today are known as safeguard methods because these are so simple that they are always going to work and they do not have any problem with divergence and so on, which may sometime happen if you use a derivative based technique. So in many cases people don't use derivative based techniques in these kind of step size determination methods because you don't want any algorithm to crash at this particular stage. Now, of course, you saw that this method is proceeding pretty slowly and it's a very basic method. So you will see that if you want to, for example, get the solution to maybe 7 or 10 decimal places, you are going to take a very long time to get there because the deltas are coming down, but then you have to calculate the function values at all those different locations of delta. For example, delta 2 delta 3 delta, which keeps coming up, and the smaller the number becomes, it essentially the grid becomes very fine. So that's one of the problems with this method. Now where this method is used is that it can sometimes be used to bracket the minimum point. So you may do 1 round of this method or 2 round of this method, and then you can switch to a different method such as the golden section method, or you can switch to quadratic interpolation or some such method which we are going to discuss in the next few videos. Now, one of the things to remember is that there are some methods out there in gradient descent where the line search needs to be very good or very detailed, or it should be valid to quite a lot of decimal points. Now, in those methods, you need to be sure that you use a method which converges well, which converges quite rapidly, rather than a method like the one we are discussing today. But today's method is useful if you have a function or a method which is pretty much okay with the line search which is not very good, and then you can just get some number like we got 0.35 in this case, and we can proceed with that. You do not need to get 0.3517 and so on. But again, there are some methods, for example conjugate gradient methods, specifically some conjugate gradient methods such as Fletcher-Reeves, where you need to have a pretty good or an exact line search, and in those cases you need to make sure that you converge to a pretty decent number out there before you move that much amount in the search direction. So that's something to keep in mind. So I will end this lecture today. Again, make it a point to look at the optimization lecture 7, where you will find the details about this method, and also take a look at the optimization playlist to learn more about optimization techniques. And of course, there are guys out there who may be able to write much better Python code. So in case you find that the algorithm has any issues, it may be not the best algorithm out there, not the best implementation, you can write pieces or snippets of your code or correct my code in the comment section. So I'll welcome any statements like that. And I will see you in my next video sometime soon.